Tonight, we are venturing together toward the edge of understanding. We're going to approach one of the most mysterious, most powerful, and most misunderstood creations in all of existence. We are going to explore the slow, deep, and profound patience of a black hole. It feels like a strange word to pair with such an object, doesn't it? Patience. Our modern stories have painted them as things of immense speed and cosmic violence, insatiable monsters lurking in the dark, devouring stars and worlds without a thought. But that is only the loudest part of their story. Tonight, we are going to listen for the quiet part, the part that has more to do with stillness than with speed, more to do with the slow passage of eons than the fleeting moment of consumption. We are going to learn how a black hole waits. But before we allow ourselves to fall into this gentle gravity of thought, I would love for you to take a quiet, conscious moment for yourself. Settle into your space. Feel the support of the surface beneath you. And just for a moment, consider what the feeling of patience is like in your own body right now. Is it the soft, quiet space between your in breath and your out breath? Is it the feeling of your muscles letting go of the day's tensions one by one? Is it the quiet, hopeful anticipation of a deep and peaceful night's sleep? Whatever that feeling is for you, I invite you to hold it gently, to cradle it in your awareness as we begin our journey. If you find that this exploration helps to quiet the busy traffic of your mind, if it helps to soothe your thoughts into a gentle drift, I would be ever so grateful if you offered the video a like and perhaps subscribed to our channel. It helps this peaceful harbor of cosmic calm reach other souls who might be searching for a moment of quiet in the long, dark night. And please remember that there is no pressure here, no expectation to stay with me until the very end. If my voice becomes a gentle, monotonous drone, and these cosmic ideas become a soft pillow for your tired mind, then our journey together has been a wonderful success. If you stay awake, you may learn something that fills you with a sense of wonder. If you drift off into slumber, you will have found the rest you deserve. There is no wrong way to be here with me tonight. So now, let your body grow heavy. Feel it sinking softly into a state of perfect rest. Let the day, with all its worries and its lists, fall away from you. Let it collapse behind you like a distant, dying star. And let's travel together on a current of thought to a place where time itself learns how to wait. Our story, strangely enough, begins not in the depths of space, but in the depths of the human psyche. It begins with our ancient and unshakable fascination with darkness. For as long as we have possessed a conscious mind, we have been both drawn to and frightened by the void. The deep, dark, silent ocean, holding unknown worlds beneath its surface, the unlit cave, a doorway into the Earth's secret heart, the starless patch of a cloudy night sky where the familiar, friendly lights have vanished, leaving only a profound and unsettling emptiness. There is something primal in that darkness. It is the place of the unknown, the canvas upon which we paint our greatest fears and our most hopeful myths. And for most of human history, we looked up at the night sky and saw it as a place of light alone, a celestial tapestry woven with the brilliant silver threads of suns and galaxies. The darkness was just the background, the empty stage upon which the cosmic drama unfolded. But even 2 centuries ago, a few quiet, thoughtful minds began to wonder, could the darkness itself be a thing? Not just the absence of light, but an active, physical presence? Could there be objects in the heavens whose very nature was to be dark? This revolutionary idea took root in the mind of a man named John Michell, an English parish rector and natural philosopher living in the late 1700s. He was a man of quiet contemplation, living in a world still governed by the elegant and predictable clockwork physics of Isaac Newton. In Newton's universe, gravity was a simple, dependable force, an invisible string pulling objects toward one another. Space was a fixed, unchanging stage, and time was a universal clock, ticking along at the same steady pace for everyone, everywhere. Michel was fascinated by Newton's work and by a concept known as escape velocity. It is a simple but profound idea. If you throw a ball into the air here on Earth, it will go up, but gravity will inevitably pull it back down. However, if you could throw that ball fast enough, at about 25,000 miles per hour to be precise, it would overcome Earth's gravitational pull completely and fly off into space, never to return. That speed is Earth's escape velocity. Michel reasoned quite logically that a star, being much, much more massive than the Earth, must have a much, much, much higher escape velocity. And then, in a stroke of brilliant intuition, he asked the question that would echo through the centuries. What if a star was so massive and so incredibly dense that its escape velocity was faster than the speed of light itself? It was an astonishing thought. Light, the fastest thing in the entire known universe, would be like that ball thrown up from the star's surface. It would leap from the star, travel for a brief moment, but the star's immense gravity would be an unbreakable chain. The light would slow, stop, and fall back down onto the star it had just tried to leave. The star would be completely invisible to the outside universe. It would be a dark star, a ghost in the cosmic machine, hidden in plain sight, its own light trapped as a prisoner of its own immense weight. The idea was so radical, so far outside the comfortable clockwork of Newton's world, that it was largely dismissed and forgotten for over 150 years. It remained a curious footnote in the history of science, a clever thought experiment from a country parson, but nothing more. The universe, it seemed, was a place of light and order and had no room for such dark and paradoxical monsters. But the universe, it turned out, held secrets far stranger than even Jean Michel could have imagined. And the key to unlocking those secrets would come from a place no one expected, the mind of a young patent clerk in Bern, Switzerland, a man who would forever change our story of reality. His name was Albert Einstein. In the early years of the 20th century, Einstein gave the world a new story about the universe, a new vision of space, time, and gravity. He called it his theory of general relativity. And in this new story, gravity was not a force at all. It was not an invisible string pulling things together. Instead, Einstein revealed gravity was the very shape of reality itself. I want you to imagine, just for a moment, that space and time are not separate things. Imagine they are woven together into a single, vast, flexible fabric, a four-dimensional cosmic trampoline that stretches across all of existence. Now, every object that has mass, a planet, a star, your own body, as you rest here now, creates a small dip, a gentle depression in this fabric of space-time. The more massive the object, the deeper the dip. What we feel as gravity, according to Einstein, is simply the effect of this curvature. A planet orbits the sun not because it is being pulled by some mysterious force, but because it is rolling along the inside of the great, gentle curve that the sun's immense mass creates in the fabric of space-time. It is following the straightest possible path through a curved reality. This theory was a masterpiece of human thought. It was beautiful. It was elegant, and it described the workings of the universe with a breathtaking accuracy that Newton's laws could not match. But hidden deep within Einstein's elegant equations, there was a secret, a dark and disturbing prediction that troubled Einstein himself. The mathematics suggested that if you could take a massive enough star and squeeze it down into a small enough space, the curvature of space-time around it wouldn't just be a gentle dip anymore. It would become a puncture, a tear, a bottomless well from which nothing, not even light itself, could ever escape. The fabric of space-time would be so severely warped that it would in effect fold in on itself and close off from the rest of the universe. The dark star of Jean Michel was back, but this time it was something far more terrifying and profound. It wasn't just a star that light couldn't leave. It was a place where space and time as we know them came to a screaming halt and ceased to exist. It was a point of infinite dense zero volume. It was a singularity. Einstein, a man who believed in an orderly and predictable universe, disliked this idea immensely. It seemed too extreme, too messy, a breakdown in the beautiful cosmic order his theory had revealed. He hoped it was just a mathematical quirk, something that wouldn't happen in the real world. But the universe, it turns out, is not always gentle. Sometimes it is extreme, and sometimes, in the fiery death of a giant star, it creates a black hole. So let us now approach this object with our minds. Let's build one together, not with collapsing stars and impossible physics, but with quiet contemplation. Let us trace its anatomy piece by peaceful imaginary piece so that we might understand its nature. At the very, very heart of it all, hidden forever from our view, is the singularity. It is a word we are forced to use to describe something that our language and our mathematics cannot truly contain. It is the final destination of every single particle of matter and every single photon of light that falls into a black hole. It is, according to the theory, the place where the entire mass of a collapsed star, sometimes many, many stars, is crushed into a region of zero physical volume and therefore infinite density. Here, at this one single point, our most fundamental laws of physics simply break down. The equations that describe our universe with such precision everywhere else suddenly return answers of infinity, which is the universe's polite and mathematical way of saying, I have no idea what is happening here. It is the end of place. It is the end of time. It is the ultimate unknown, a final, quiet mystery that the universe keeps entirely to itself. So think of it not as a terrifying point of destruction, but as a place of perfect and perpetual mystery. But we can never ever see the singularity directly. It is protected, it is hidden behind a perfect, invisible, one way veil. This sacred boundary is called the event horizon. This is perhaps the most famous and most misunderstood part of a black hole. The event horizon is not a physical surface. You would not bump into it if you were to travel there. It is not a wall made of matter or a shimmering energy field. It is simply a boundary in spacetime, a line of demarcation. It is the point of no return. I want you to imagine a wide, powerful river. At its source, the water flows gently, and you could easily swim or paddle a boat against the current. But as the river flows, it gets narrower and steeper, and the current grows stronger and stronger. Eventually, you would reach a point in the river where the water is flowing so fast that no matter how hard you paddled, no matter how powerful your boat's engine was, you could no longer escape the pull of the current carrying you toward the great waterfall ahead. You are not trapped by a wall. You are trapped by the flow of the river itself. The event horizon of a black hole is exactly like that line in the water. It is the point in space-time where the inward flow of space itself is pulling you toward the singularity faster than the speed of light. And since nothing in the universe can travel faster than light, once you cross that invisible threshold, there is no escape. Not by any means. Not ever. It is a silent, calm, and utterly irreversible transition, a one-way door into forever. And it is here, at this quiet, invisible boundary, that time, our old and familiar companion, begins to play its most extraordinary and patient trick. As we were saying, it is here, at the quiet, invisible boundary of the event horizon, that time itself begins to warp and bend in the most profound way imaginable. According to Einstein's theory of general relativity, strong gravity has a powerful effect on the passage of time. The stronger the gravitational field, the slower time flows. This isn't just a theoretical idea. It is a real, measurable fact of our universe, a subtle but constant feature of our daily lives. The clocks aboard the GPS satellites that orbit high above the Earth are in a slightly weaker gravitational field than we are down here on the surface. Because of this, their internal clocks actually run a tiny fraction of a second faster than our clocks on the ground. To keep the entire GPS system from falling into chaos, their timing has to be constantly and precisely adjusted to account for this strange relativistic effect. Your ability to find your way to a new coffee shop is, in a very real sense, a daily proof of Einstein's genius. Now, take that subtle effect and amplify it beyond all comprehension. Imagine the gravity near a black hole's event horizon. It is not just strong, it is almost infinitely powerful. And so its effect on time is not subtle, it is absolute. Let us imagine a thought experiment, a gentle one. Picture a brave astronaut, a friend of yours, who decides to make the journey toward a large black hole while you remain behind, watching from the safety of your spaceship far, far away. You both have perfectly synchronized clocks, and you maintain a constant communication link. As your friend begins their descent, their journey toward the event horizon, something remarkable would begin to happen from your point of view. At first, the changes would be small. You would notice their clock beginning to tick just a little bit more slowly than yours. The messages they send back to you would arrive with slightly longer and longer delays, their voice sounding deeper and slower, stretched out by the growing gravitational pull. As they get closer and closer to that invisible threshold, the effect would become extreme. You would see their clocks slow to a crawl. Minutes for them would become years for you. Years for them would become centuries. Their every movement would become a slow motion ballet of impossibility. You would see them seem to hover there, right at the edge of the abyss, frozen in time. The light from their spaceship would become redder and dimmer, a phenomenon known as gravitational redshift. Gravity is literally stealing the energy from the light photons as they struggle to climb out of the black hole's immense gravitational well. Their image would fade, stretching and reddening until it vanished completely, not because they have fallen in, but because the last photon of light from their ship has lost all its energy on its journey to your eyes. From your perspective, watching from the safe distance of your ship, your friend would never, ever cross the event horizon. You would watch them approach it for the rest of your life and for the lives of your children and their children's children for an eternity. They would be frozen forever on the edge of forever. Their now and your now would have become two completely different, irreconcilable things. This is the patience of a black hole made manifest. It does not just wait in time, it forces time itself to wait at its doorstep. But what about the experience of your friend, the astronaut? For them, there would be no drama, no slowing down. Their own clock would tick along at a perfectly normal rate. They would feel their body aging, their heart beating, their thoughts flowing at their usual pace. They would look back at you, and from their perspective, it would be your clock and the clock of the entire universe that was speeding up, racing toward the future at an incredible rate. They would see the stars of the distant cosmos whirl and age and die in what feels to them like a mere matter of hours. And then at a very specific and uneventful moment, they would cross the event horizon. There would be no sign, no jolt, no flash of light. The space around them would look no different than it did a moment before. But at that instant, their fate would be sealed, absolutely and irrevocably. They have passed through the one way door. Inside the event horizon, the very of space time is so profoundly warped that the rules of reality are rewritten. Here, the direction toward the singularity is no longer a direction in space, it becomes a direction in time. It becomes the future. Just as you, here on Earth, cannot help but move forward into tomorrow, our astronaut, once inside the event horizon, cannot help but move toward the singularity. Every possible path, every direction they could try to move in, leads only to the center. To try and move away from the singularity would be like trying to travel back in time to yesterday. It is a physical and temporal impossibility. Their final journey would be a quiet one. For a very large, supermassive black hole, the tidal forces at the event horizon are actually quite gentle. They could fall for a long time, perhaps hours, in a state of peaceful freefall, seeing the universe they left behind condensed into a single bright point of light above them. But eventually, as they approached the central singularity, the tidal forces would become unimaginably strong. This is the process that scientists with a touch of grim poetry call spaghettification. It sounds playful, but it describes the ultimate deconstruction. The gravitational pull on the part of their body closer to the singularity would become so much stronger than the pull on the part of their body further away. This immense difference in gravity would gently but inexorably stretch them out, longer and longer, thinner and thinner. First their body, then their cells, then the very molecules that made them up would be elongated into a thin, single file stream of fundamental particles flowing like a river into the central mystery. It is not so much a violent destruction as it is an ultimate unraveling. A final, intimate return to the basic ingredients of the cosmos as the universe gently pulls them back into its most elemental form. For a very long time in the history of our understanding, this was the entire story of a black hole. They were cosmic endpoints, gravitational tombs, the dark, quiet, and eternal remnants of massive stars that had lived out their brilliant lives and had now collapsed into these perfect prisons of space-time. They were fascinating, to be sure, but they were seen as passive objects, the final full stops at the end of a cosmic sentence. But as our tools for observing the universe grew more powerful and our theories grew more sophisticated, we began to discover that this was far from the whole truth. We began to see that black holes are not just passive endings, they are also powerful engines of creation. They are the great gardeners of the cosmos. We discovered that at the very center of almost every large galaxy we can see, including our own beautiful Milky Way, There lies a sleeping giant, a supermassive black hole. These are the true titans of the universe. They are not the remnants of a single collapsed star. They are cosmic behemoths, millions or even billions of times more massive than our sun. We are still not entirely sure how they form, but we believe they are ancient objects that have grown over the course of eons by slowly and patiently swallowing immense clouds of gas, countless stars, and even other smaller black holes that stray too close. These supermassive black holes are not just sitting there idly in the galactic center. They are the anchors of their galaxies. Their immense gravity is the calm, silent eye of a cosmic hurricane around which hundreds of billions of stars, including our own sun, revolve in a slow, majestic cosmic dance. They are the silent, invisible shepherds of their galactic flocks, and their influence is profound. They are cosmic gardeners, shaping the evolution of the galaxies they inhabit in ways we are only just beginning to understand. Sometimes their immense gravitational pull can stir up vast, cold clouds of interstellar gas, compressing them and triggering a magnificent frenzy of new star birth, lighting up their galaxies with the fire of a new generation of suns. At other times, their role is even more dramatic, as vast quantities of matter, gas, dust, entire stars are drawn toward the supermassive black hole. It doesn't just fall straight in. Instead, it forms a vast, flat, swirling structure around the black hole, a cosmic whirlpool called an accretion disk. This disk can become one of the brightest and most energetic things in the entire universe. As the matter spirals ever closer to the event horizon, it is accelerated to nearly the speed of light. The friction and compression within the disk heat the gas to millions or even billions of degrees, causing it to blaze with a light that can outshine all the hundreds of billions of stars in its host galaxy combined. An object that is fundamentally dark, a hole in reality, becomes the engine for the most brilliant beacon of light imaginable. This radiant phenomenon is known as a quasar, and these are the lighthouses of the deep, early universe, visible to us across billions of light years. And so we have the ultimate cosmic paradox. The darkest object in existence becomes the catalyst for the most brilliant light. A black hole, in its quiet gravitational patience, creates a spectacle of such power that it can be seen from the very edge of the observable universe. It is a testament to the strange and beautiful way that the cosmos weaves together creation and destruction into a single inseparable story. And yet, the story gets stranger still. For most of the 20th century, the one unbreakable rule of a black hole was that nothing, absolutely nothing, could ever escape from beyond the event horizon. They were perfect, eternal prisons. But then in the 1970s, a brilliant and determined physicist named Stephen Hawking was deep in thought, trying to do something that had never been done before. He was trying to unite the two great pillars of modern physics: Einstein's general relativity, the science of the very large, and quantum mechanics, the strange and ghostly science of the very small. And in that difficult and abstract marriage of theories, he stumbled upon something that no one, not even he, had ever expected. He found that black holes are not completely black after all. He discovered that they have a faint, almost imperceptible temperature. And if they have a temperature, it means they must glow. He discovered that black holes, against all odds, leak. This phenomenon, which would later be named Hawking radiation in his honor, is one of the most profound and mind bending ideas in all of modern physics. It is a concept born from the strange and ghostly world of quantum mechanics, a world that operates on rules that seem to defy all common sense. To understand it, we must first adjust our perception of emptiness. We tend to think of empty space, the vacuum, as being truly and completely empty, a perfect nothingness. But quantum mechanics tells us a different story. It tells us that the vacuum of space is, in fact, a bubbling, fizzing, chaotic sea of energy. It is a place of constant activity where tiny pairs of virtual particles spontaneously pop into existence from nothing, exist for an immeasurably brief moment, and then annihilate each other, disappearing back into the nothingness from whence they came. One of these particles is made of matter, and the other is its opposite, made of antimatter. They are born together as a pair, and they die together, their existence a fleeting, balanced loan from the universe's energy budget. This happens everywhere, all the time, in every cubic centimeter of space around you right now. The universe, at its most fundamental level, is not still. It is a shimmering, seething foam of potential. Now, Hawking asked a very clever question. What would happen if one of these virtual particle pairs happened to pop into existence right at the very edge of a black hole's event horizon? Imagine this tiny, fleeting drama unfolding on that invisible precipice. A particle and its antiparticle are born from the vacuum. In the infinitesimally small moment before they can annihilate each other, the black hole's immense gravity intervenes. It is possible for one of the particles to be captured, to fall across the event horizon, while its twin partner manages to escape, flying off into space. The particle that falls into the black hole has what we call negative energy relative to the universe outside. This is a strange but necessary concept from quantum physics. When it falls in, it effectively reduces the total mass and energy of the black hole by a tiny, tiny amount. Meanwhile, the particle that escaped becomes a real particle, no longer virtual. It flies away into the cosmos, carrying a tiny bit of positive energy with it. To an observer watching from a safe distance, it would look as though the black hole itself had just emitted a particle. It would appear to be glowing ever so faintly. It would be radiating. This process is so unbelievably slow and subtle that it is almost impossible to imagine. It is the quietest whisper in the entire universe. For a black hole with the mass of our sun, the amount of energy it radiates away would be far, far less than the energy it absorbs from the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. Such a black hole is actually growing, not shrinking. But this faint leakage, this slow, patient evaporation, hints at something astonishing. It means that black holes are not, in fact, eternal prisons. They are not forever. They have a finite lifespan. And this realization leads us to a concept of time so vast that it makes our minds reel. It is here that we truly begin to understand the patience of a black hole. Let's try gently to wrap our minds around these timescales. The age of our entire universe, from the Big Bang until this very moment, is roughly 13.8 billion years. It is a number so large it's difficult to feel. But let's use it as our measuring stick, 1 unit of cosmic time. Now, consider a black hole with the mass of our sun. According to Hawking's equations, the time it would take for this black hole to completely evaporate, to radiate away its entire mass particle by patient particle, is not thousands or millions or billions of years. The time required is approximately 10 to the power of 67 years. Let us pause there. A 1 followed by 67 zeros. There is no analogy that can do justice to this number. If you were to represent the entire 13.8 billion year lifespan of our universe as a single grain of sand, the time it would take for that solar mass black hole to evaporate would not be a beach or a desert or all the sand on Earth. It would be a sphere of sand so large it would fill our entire solar system and then some. The entire history of our universe is an insignificant, fleeting blink of an eye in the life of a single small black hole. And what about the supermassive giants that live at the heart of galaxies? A black hole with the mass of a billion suns would take even longer. Its lifespan is estimated to be around 10 to the power of 100 years, a number so large we call it a googol. It is a 1 followed by 100 zeros, a timescale so profound that it seems to touch the face of eternity itself. This is the ultimate cosmic patience. A black hole will sit in the cold and the dark of a dying universe, long after the last star has faded, long after the last planet has crumbled to dust, and it will wait. It will slowly, silently, particle by patient particle, radiate itself away into nothing. It is waiting for the end of an era that has not yet even begun. It is waiting for the end of time itself. And this incredible, almost unbelievable idea leads us to our final destination for this part of our journey tonight, a speculative voyage into the deep, deep future of the cosmos. What will the universe look like when the patient reign of the black holes is the only story left to tell? To do this, we must let go of our human scales of time. We must let go of days and years and even millennia. We must think in eons. So let's travel forward in our minds, far beyond the familiar shores of the present. Let us journey forward 1 trillion years. By this time, the great era of star formation will be long over. The vast clouds of gas and dust from which new stars are born will have been used up. The universe will have continued its long, slow expansion, pulling the galaxies further and further apart from one another. The sky, as seen from any remaining planet, would be almost completely dark, the light from distant galaxies having stretched and faded into invisibility. The stars that are still shining will be the small, cool red dwarf stars. They are the most frugal of all stars, sipping their hydrogen fuel so slowly that they can live for trillions of years. But even they will not last forever. One by one, they will finally exhaust their fuel and fade into cold, dark remnants called black dwarfs. By about 100 trillion years from now, the stelliferous era, the great age of starlight that we are so lucky to live in, will be over. The last light from the last star will have gone out. The universe will become a cold, dark, and profoundly empty place. It will be a realm of ghosts, populated only by the cooling embers of dead stars, neutron stars, white dwarfs, and the silent, patient black holes still waiting. This next great chapter in the life of the cosmos is sometimes called the degenerate era. For a period of time that again beggars the imagination, these dead stars will be the most prominent objects in the universe. They will continue to orbit the centers of their ghostly, dark galaxies, but even they are not eternal. Over truly stupendous timescales, quantum mechanics will play another strange trick. A phenomenon called proton decay, if it is real as some theories suggest, will cause the very matter of these dead stars to slowly dissolve. Protons, the building blocks of atoms, will decay into lighter particles and radiation. Slowly, atom by atom, these stellar remnants will simply vanish, like a sugar cube dissolving in an infinite ocean of time. This process is even slower than the evaporation of black holes, but it will happen. And so, after a period of perhaps 10 to the power of 40 years, even the dead stars will be gone. The universe will have been swept clean of almost all the matter we know. And what will be left? Only the black holes. This is when the true black hole era begins. For a period of time that stretches from 10 to the power of 40 years, all the way up to that unimaginable number, 10 to the power of 100 years, these objects will be the last remaining organized large scale structures in the entire cosmos. They will be the quiet, solitary kings of a dark and silent empire. Their immense gravity will be the only significant force still shaping the void. The universe will be a quiet place then, a place of deep, profound rest. The frenetic energy of the early cosmos will be a forgotten memory. The warmth and light of the stars will be a legend from an impossibly ancient past. There will only be the cold, the dark, and the patient waiting of these gravitational titans. And then, one by one, over those googles of years, they too will begin their final, graceful act of disappearing. The smallest black holes will evaporate first, then the mid sized ones, and finally, the great supermassive giants that once anchored the galaxies. Imagine the very last supermassive black hole in the entire universe. It has outlasted everything. It is the last remnant of structure, the last complex thing in a cosmos that has become utterly simple. And it too begins its final exhalation. For countless eons, it radiates away its final stores of mass and energy, releasing them back into the void as a final, faint, gentle whisper of low energy light and other fundamental particles. And then one day, in a final, quiet pop of energy, it too will be gone. The last organized structure in the universe will have vanished. What remains is a state that physicists call the heat death of the universe. It is a future so alien it is hard to grasp. It will be a vast, cold, and ever expanding emptiness, filled with a thin, uniform, and incredibly cold soup of photons, neutrinos, and other stray particles. There will be no structure, no change, no complexity, no memory. The temperature everywhere will be almost absolute zero. Because there is no longer any difference in temperature or energy from one place to another, no work can be done. No processes can happen. The arrow of time, which is so dependent on the increase of entropy and the flow of energy from hot to cold, will lose all its meaning. In a universe that is perfectly uniform and still, time itself may cease to have any function. This is the predicted final state of the cosmos, not an ending of fire and fury, but one of perfect, unshakable, and eternal peace, the final, silent state of rest. The universe, having told its long, beautiful, and complex story, will finally fall completely and utterly silent. And now, with that vision of the end of all things held gently in our minds, let us begin the long journey back. back from the end of time, back from the era of the last evaporating black hole, back through the age of the dying stars, back through the trillions of years of darkness, back to our own bright, beautiful, and vibrant stelliferous era, back to our own Milky Way galaxy, our own solar system, our own small blue planet, back to this room, this bed, this singular, precious moment in time. You are here, now, breathing in and breathing out. A living, thinking, feeling being made of stardust, existing in this perfect, fleeting sliver of cosmic history when the universe is alive with light and warmth and possibility. The patience of a black hole seems so inhuman, so alien, so vast. Its timescales are beyond our comprehension, but perhaps a tiny, resonant echo of that immense patience lives within each of us. It is the part of us that knows how to be still, the part that can let go of the frantic pace of the day and simply be. The part of us that understands that all things, even the busiest of days and the most troubled of thoughts, will eventually pass. It is the part of us that knows how to wait for the gentle gravity of sleep to pull us into its own quiet mystery. So, as you lie here, I want you to feel that gentle gravitational pull of slumber. It is not something to be fought or resisted. It is a natural force like gravity itself, a call to rest, a pull toward a state of peace and renewal. Let it stretch out your thoughts like light from a distant star until they are long and thin and quiet. Let time slow down for you here in the calm sanctuary of your own small universe. There is nothing left for you to do tonight. Nowhere else you need to be. No problem you need to solve. All that is left is to let go. But before we fully let go, before we allow ourselves to drift completely into that state of peaceful rest, there is one last mystery to consider. One final deep question that the patient existence of a black hole asks of the universe. It is a question so profound that it has troubled physicists for decades, and it touches upon the very nature of reality, of information, and of memory itself. It is known as the black hole information paradox. In physics, there is a fundamental rule, a core principle of quantum mechanics, that is considered almost sacred. It states that information can never be truly destroyed. Information, in this sense, isn't just words or numbers. It is the specific, unique quantum state of every particle in the universe. It is the universe's own perfect memory of itself. You can burn a book, but in theory, if you could capture every single particle of smoke, every photon of light, every bit of heat, you could reconstruct the book exactly as it was. The information is scrambled, not erased. This principle of conservation of information is a bedrock of our understanding of the cosmos. But a black hole presents a profound challenge to this rule. Imagine you throw something into a black hole. Let's say that book. The book is made of particles, and those particles contain a vast amount of information: the type of atoms, their arrangement into paper and ink, the specific story written on the pages. All of that unique, specific information falls across the event horizon. From the outside world, it is gone forever, hidden behind that one way door, destined to be crushed into the central singularity. For a long time, this wasn't a major problem. Physicists could simply say that the information wasn't destroyed, it was just locked away inside the black hole, inaccessible but still technically there. The universe's memory was safe, just stored in a vault from which nothing could ever return. But then Stephen Hawking made his startling discovery. He showed us that black holes evaporate. Over those unimaginable eons, they leak Hawking radiation and eventually disappear completely. And here is the paradox. The Hawking radiation that is emitted seems to be completely random. It is thermal radiation, like the gentle heat coming off a warm object. It doesn't seem to contain any of the specific, complex information about the things that fell into the black hole in the first place. The particles that come out seem to have no memory of the book that went in. So, what happens when the black hole has finished evaporating? When it has completely vanished, taking the singularity with it? Where did the information go? If the information is truly gone, destroyed forever, then one of the fundamental pillars of modern physics is wrong. It would mean that the universe has a kind of amnesia, that it can forget how things were. It would mean that the predictable, orderly evolution of the cosmos has a fundamental leak in it. This is a possibility so disturbing that most physicists are reluctant to accept it. On the other hand, if the information does somehow escape, how does it get out? How can it pass through the event horizon, a boundary that we believe is absolutely impassable from the inside out? Does the Hawking radiation somehow carry the information in a subtle, scrambled form that we just don't understand yet? Does the information get imprinted on the event horizon itself, like a kind of cosmic hologram? This is the information paradox, and it is one of the biggest unsolved mysteries in theoretical physics. It is the place where our two greatest theories of the universe, general relativity and quantum mechanics, clash most violently. It tells us that there is something deep and fundamental about reality that we are still missing. Some physicists, including Hawking himself late in his life, came to believe that the information is not lost. They propose that it is stored on the surface of the event horizon, a two-dimensional surface that holographically encodes all the information of the three-dimensional objects that have fallen in. When the black hole evaporates, this information is then slowly and subtly encoded back into the outgoing radiation. The universe's memory is preserved, just in a very scrambled and unexpected way. Other, more radical ideas suggest that the information escapes through tiny microscopic wormholes, or that what we see as a black hole is actually a fuzzball, a tangled string theory object with no true singularity at all. Or perhaps, in the final moments of a black hole's evaporation, a remnant is left behind, a tiny, stable nugget of information from everything it ever consumed. We do not yet know the answer, and perhaps we never will. But the question itself is a beautiful one. It reminds us that the universe is not just a collection of matter and energy, but also a story written in the language of information. And it asks us whether that story can ever be truly erased. The patience of a black hole, then, is not just about waiting to evaporate. It is also the patience of holding on to the universe's greatest secrets. It waits, holding the memory of fallen stars and ancient books, challenging us to understand the fundamental rules of existence itself. It is a quiet, dark, and persistent question mark hanging in the cosmos, inviting us to wonder, to dream, and to be humbled by the depth of what we do not know. And now, with that final, deep mystery held gently in our thoughts, let us bring our long journey to a close. Let us bring our awareness back, once and for all, back from the edge of the paradox, back from the heart of the quantum foam, back from the immense patient darkness. Let's come back to this room, to this moment, to the simple, profound reality of your own body, resting. Feel the gentle weight of your limbs. Notice the soft fabric against your skin. Become aware of the slow, steady, rhythmic pattern of your own breathing. Inhale and exhale. Each breath is an anchor to the present moment, a tiny personal tide, pulling you away from the vast ocean of cosmic thought and into the safe harbor of your own being. The universe is a place of unimaginable scale and complexity. It contains concepts of time that can break our minds and paradoxes that challenge the very nature of reality. And yet here you are, a part of it all, a conscious piece of the cosmos, capable of contemplating these immense mysteries from the quiet safety of your bed. You are a vessel of stardust, a temporary arrangement of ancient atoms that has been granted the astonishing gift of awareness. And now, the time for awareness, for thinking, for wondering, is gently coming to an end, at least for tonight. The patience of a black hole is a cosmic lesson. It teaches us about the beauty of letting go. It shows us that even the most powerful and complex things in the universe eventually yield to a state of simplicity and peace. It reminds us that there is a profound stillness waiting at the heart of all things. And so, I invite you now to embrace your own little piece of that cosmic patience. The patience to let the day truly end. The patience to let your thoughts dissolve without judgment, like virtual particles disappearing back into the quiet void. The patience to trust in the restorative power of darkness and silence. There is nothing more you need to do, no more information you need to process. The story is told, and now it is time for rest. Allow the gentle gravitational pull of sleep to be your event horizon for tonight, a soft, welcoming threshold into the world of dreams. Let go and allow yourself to fall into that peaceful singularity of slumber, where the busy world of time and space can, just for a while, cease to exist. Thank you for joining me on this journey to the quietest corners of the cosmos. I hope it has brought you a sense of wonder and a deeper sense of peace. If it has, and you feel so inclined, a like or a subscription is always deeply appreciated, as it helps this small, drowsy universe of ours to grow. But for now, all that is left is the silence. All that is left is your breath. All that is left is the deep, dark, and beautiful mystery of your own impending rest. Sleep well. Be patient with your dreams. The universe will still be here when you wake.